In August of 2012, the United States Department of Transportation and the University of Michigan Transportation Research Institute, known as UMTRI, embarked on a 12-month research project called the Safety Pilot Connected Vehicle Model Deployment in Ann Arbor, Michigan. The model deployment brought together transportation experts from government, academia, and the private sector to test the potential of connected vehicle technologies to reduce vehicle crashes, the leading cause of death for Americans between the ages of 4 and 35.
Safety. How do we make driving safer? How do we save more lives? How do we save more injuries? All of us coming together around that very important agenda.
Connected vehicle technologies allow vehicles to communicate with one another, so drivers can receive important safety information about the vehicles near them, such as hard braking several cars ahead. Vehicles communicate wirelessly through dedicated short-range communications, or DSRC, which is similar to Wi-Fi. This communication broadcasts a basic safety message about each vehicle 10 times per second. The message includes GPS location, speed, heading, transmission state, brake status, steering wheel angle, path history, and path prediction. DSRC has a range of about 300 meters, and the information shared among vehicles is handled anonymously and securely. Connected vehicle technologies have the potential to prevent an estimated 80% of non-impaired crashes, saving thousands of lives and preventing millions of injuries by providing drivers with advanced warning about dangerous situations. The application of these technologies could have the biggest impact on motor vehicle safety since seat belts and airbags. After years of research and progress with connected vehicle technology, what no one knew was how a large test case of real drivers on real roads would respond to these technologies, and how the technologies themselves would hold up in real-world situations, until now. UMTRI, a University of Michigan institute with over 100 researchers and supporting staff committed to safe and sustainable transportation, was selected to be the test conductor for the Safety Pilot Model Deployment. In this role, UMTRI was responsible for implementing the largest deployment of connected vehicles in the world. The objectives were to demonstrate connected vehicle technologies in a real-world multimodal environment, determine driver acceptance of vehicle-based safety systems, evaluate the feasibility, scalability, security, and interoperability of DSRC, and assess options to accelerate safety benefits. The U.S. DOT provided funding for the model deployment as well as technical support through a number of its branches. Numerous partners and suppliers also supported the deployment, including a collaboration of 8 automakers, known as CAMP, which provided vehicles and technical support for the project. The model deployment consisted of 8 tasks, taking place over 3 years between August 2011 and August 2014. Data was supplied to U.S. DOT throughout the program. To represent a real-world deployment, connected vehicle technologies were installed in diverse makes and models of more than 2,800 cars, trucks, buses, and motorcycles. The CAMP automakers provided 64 vehicles to the participant drivers. The vehicles contained a variety of integrated connected vehicle technologies, including audio and visual warnings. For the remaining vehicles, UMTRI fitted participants' personal vehicles with one of 3 types of connected vehicle technologies. 2,450 vehicles were fitted with a vehicle awareness device. This device wirelessly and securely transmitted a basic safety message approximately 10 times per second. These vehicles did not receive messages or provide warnings to drivers. 215 vehicles were fitted with an aftermarket safety device. This device not only transmitted basic safety messages, but also received the messages from other vehicles, which it used to provide drivers with audio warnings if the threat of a crash existed. 115 vehicles were fitted with both an aftermarket safety device and a data acquisition system. The data acquisition system collected video and data on driver performance, so researchers could learn how drivers interacted with the safety devices and how they responded when crash warnings were presented. The data acquisition system included a data recorder, an interior dual-band antenna for GPS and cellular reception, a front-facing range-sensing camera and module for measuring lane position and distance to the vehicle ahead, an inertial measurement unit for detecting acceleration, inclination, and yaw rate, a microphone and recording equipment, and 4 video cameras, 1 forward-facing, 2 rear-facing, and 1 in-cabin camera, capturing the driver's face and including infrared illuminators for nighttime driving. A number of installation facilities were used to install devices in participants' personal vehicles, including one constructed at UMTRI, where devices were installed on more than 2,500 vehicles. UMTRI also developed a property and configuration management tool that was used to track all equipment mounted in the vehicles and to prepare configuration files for both the aftermarket safety device and the data acquisition system. All devices were labeled with an ID and pictures were taken to document each vehicle after installation. No permanent modifications were made to the vehicles. The Safety Pilot Model Deployment Testbed site includes 3 major east-west corridors in Ann Arbor, along with portions of the highways of M14 and US 23. The site encompasses 72 lane miles of roadway that provide a mix of city streets and highways, offer a wide range of traffic volumes, and are consistent with participants' daily commutes. Additionally, there are high-volume origin and destination centers in the deployment area, such as healthcare centers and hospitals, primary and secondary schools, institutions of higher education, and other major employers. DSRC roadside equipment was installed at 19 intersections, 3 curve sites, 3 freeway sites, and 1 site at UMTRI, chosen for optimal interactions and coverage from a single antenna. The roadside installations consisted of 1 or 2 DSRC radios and antennae. All roadside installations had a minimum radio range of 300 meters in all directions, and many had a much greater range, in some instances reaching over 1,000 meters. The arterial DSRC sites were connected directly to the city's fiber optic network, whereas freeway sites were connected to the city's network by wireless broadband backhaul communications. Other roadside equipment at the sites provided a communications link for data collection and distributed security certificates for the transmission of wireless DSRC messages. The Safety Pilot Model Deployment tested a variety of safety applications made possible by the DSRC test environment. The applications provided drivers with warnings that were audio, visual, or a combination of both, depending upon the type of equipment installed in the vehicle. A blind spot and lane change application cautions drivers when other vehicles enter their blind spot and increases to a warning if the drivers begin to change lanes. A forward collision application warns drivers of a potential rear-end crash due to a slowing or stopped vehicle ahead. An emergency brake lights application warns drivers about hard braking vehicles ahead that they may not be able to see. An intersection movement assist application warns drivers that it is not safe to enter the intersection due to a vehicle crossing in the other direction. A do not pass application warns drivers that it is not safe to pass due to oncoming traffic. And a left turn assist application warns drivers that it may not be safe to proceed with a left turn due to oncoming traffic. Although the primary purpose of infrastructure components deployed in the testbed area was to support vehicle-to-vehicle or V2V communications, vehicle-to-infrastructure or V2I components were deployed as well, allowing vehicles to communicate with roadside equipment. Safety applications relying on V2I communications included a curve speed application, which warns drivers of a curve location and whether the driver is exceeding the posted speed limit. A pedestrian detection application, which warns transit vehicle drivers when a crosswalk button has been pressed and when a pedestrian is in the crosswalk. And an ice warning application, which warns drivers about icy roadway conditions. Additionally, roadside equipment broadcasted the traffic signal phase and timing, which provided information about the signal color and length of time the signal would stay that color for a particular lane of traffic. This capability can be used for future V2I applications when developed and deployed. Through a unique partnership with the Ann Arbor Public Schools and Mott's Children's Hospital, volunteer drivers were selected from a broad community base to achieve a variety of origin-destination combinations within the model deployment area. A website was set up to collect participant information, and based upon their vehicle, different equipment options were available for installation. Training was provided to all participants to familiarize them with the equipment. Each vehicle was assigned a unique ID to distinguish it for data analysis. Each time vehicles interacted with one another or with the roadway around them, data was collected for analysis. The data retrieved included driver and vehicle information recorded by the data acquisition system and basic safety messages with date and timestamp logged by the vehicles and collected by roadside equipment. In addition to vehicle and roadside data, contextual data was taken from the City of Ann Arbor and weather-related sources in the area. The Safety Pilot model deployment culminated in the capturing of more than 72 billion basic safety messages. The U.S. DOT's Volpe Center led the evaluation of the data to present a more accurate and detailed understanding of the potential safety benefits of connected vehicle technologies. The data collected from the model deployment has influenced decision-making regarding the future of connected vehicles. In 2014, the National Highway Traffic Safety Administration announced that it will begin taking steps to enable vehicle-to-vehicle communication technology for light vehicles. The model deployment has provided a strong foundation for future large-scale deployments, informing the functional, technical, and legal aspects of the process. The deployment demonstrated interoperability among vehicles and suppliers, led to improved standards for safety devices, developed realistic solutions to incorporate devices into personal vehicles, advanced the understanding of how drivers will adapt to the technology, proved the viability of aftermarket devices to accelerate deployment, implemented rigorous design and installation requirements for infrastructure components, and advanced legal and policy development that is critical to user adoption. Additionally, UMTRI's outreach to the local community, private industry, researchers, the news media, and policymakers has leveraged the deployment to help elevate the connected vehicles dialogue to a regional, national, and international stage. The Safety Pilot Model Deployment Program ended in August 2014. However, UMTRI will continue to lead the operations and maintenance of the Ann Arbor Connected Vehicle Test Environment through August 2017. The goal is to support a sustainable early deployment test environment for the evaluation of new applications and associated technologies. Additionally, the University of Michigan's new Mobility Transformation Center, or MTC, will build on the model deployment's success with 3 complementary on-road vehicle deployments. MTC will expand the Safety Pilot model deployment to include 9,000 equipped vehicles and 27 square miles of equipped infrastructure in the greater Ann Arbor area. Working with the Michigan Department of Transportation and other partners, MTC will also equip nearly 20,000 vehicles from corporate and government fleets on equipped freeways in the region. And MTC will build a custom-designed integrated network of 2,000 connected, coordinated, automated, and shared vehicles. In the spring of 2015, MTC will complete the Michigan Mobility Transformation Facility, a simulated urban environment for testing connected and automated vehicles and systems before they are tried out in real traffic. Occupying 32 acres on the university's north campus, this novel test environment will include about 3 lane miles of roads, including intersections, traffic signals, sidewalks, construction barriers, and a wide range of vehicles. The Safety Pilot model deployment has been successful in helping all stakeholders understand the real-world implications of connected vehicle technologies. With a deep bench of talent, proven community support, a collaborative public-private business environment, and proximity to automakers and testbed infrastructure, Michigan is poised to continue that momentum with a regional approach to integrated, connected vehicle test beds. These deployments bring us all one step closer to realizing a day when drivers have all the information they need to avoid crashes.